Hi everyone, I'm Skanda Vivek. This course is called The Science of Everyday Materials and is intended to teach science to non-technical audiences in a fun and engaging as well as application-oriented way. I'm Skanda Vivek and I'm an assistant professor of physics here at UGC. Now, over the last decade, I've had various research experiences doing my graduate school in physics at Emory, as well as being a research fellow at Georgia Tech. And in this course, I will take my experiences in understanding the science behind various sorts of everyday phenomena, such as colloids, which are basically the particles that cause milk to be white, robot collectives, soap bubbles, and traffic jams, and more such phenomena. Apart from being a fun way to learn science, I've also had some considerable research breakthroughs, such as understanding what are the potential effects of transportation after connected vehicles are hacked. And so understanding the science behind everyday materials, such as traffic jams, can have some very important applications. So first of all, why do I keep talking about materials? So let's think about what makes up a material, right? So think about diamond. Diamond consists of um, various length scales. So at the smallest length scale, you have nucleus, and carbon atom contains a nucleus along with electrons, and these carbon atoms are arranged in a particular manner in a lattice. And this particular arrangement of carbon atoms is what gives rise to a diamond. And all of the properties of diamonds are determined from these various length scales. Now consider some other form of carbon like soot, the same thing that you get when you burn firewood. Now that sort of soot is very different from diamond, right? You wouldn't pay $10,000 for a bunch of soot, but you might pay that much for an engagement ring. Right? So are these length scales limited to just diamond or carbon or soot? No, this is something that I would unlock through this course. So first of all, we've seen materials like diamonds are composed of these various length scales from very small, the 10 to the negative 15 meters, all the way to the size of the diamond. In the same way, there are many such materials in our everyday life. Think about soap bubbles. You might think of soap as a material, and so soap bubbles contain soap molecules, and this arrangement of these soap molecules give rise to a bubble. Something that you might not consider a material is city-scale traffic jams. City-scale traffic jams are composed of road infrastructure, and on roads are vehicles. And vehicles have drivers inside them, and drivers are not perfect. So this interaction between drivers ultimately leads to traffic jams, which leads to city-scale congestion. While you might not think about materials, or you might not think of traffic as materials, it turns out the material point of view, basically understanding how large-scale properties emerge from interactions at the small scale, can actually lead to some very fundamental understanding and very important application, especially in our modern connected world. When we're connecting things together, we're having 5G, we're having vehicles that talk to each other differently from how a human would be driving. And so this sort of an understanding would help us better understand and predict the future of our societies. Right? So before that, we need to know what the scientific notation is. So scientific notation is nothing but this thing that you see up here, the 1, right? So you have 10 to the 1, that's equal to 10. What about 10 to the 2? 10 to the 2 is 10 times 10. So 10 times 10 is 100. So I hope you're starting to see a pattern here. What's 10 to the 3? Well, if this were a live audience, I'd ask you to tell me what 10 to the power 3 is. That's 10 times 10 times 10. And so that's 1,000. Now, I know that you use your calculator sometimes, and the calculator might tell you something like, if I ask the calculator, what's 10 to the 3? The calculator might say, well, it's e to the 3. Or if I ask the calculator what's 10 times 10 times 10 times 10, then the calculator might say it's e to the 4. And note, you just need to understand that e to the 4 is same as 10 to the 4. Okay? But remember, I told you the size of the nucleus is 10 to the negative 15 meters, right? So what is the negative here? Again, if this were a live class, I'd ask you to guess. And it's often fun to see what you might guess, because this is just this is a notation that we've come up with, right? So it could mean a lot of things, but this means a very specific thing. 10 to the negative 1 is 1 over 10, so that's 0.1. And 10 to the negative 15 is basically 0. So notice if there's a negative 1 here, there's 1 0 here. So if there's 15, there's a total of 15 zeros, so 0 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 meters, right? I hope I haven't missed any zeros. And that's where the scientific notation is actually important, because the human eye tends to look at this number 15 and say, well, that's pretty small. Whereas if let's say I put another 0 by mistake in there, you wouldn't know, right? If you just looked at it. But you know that 15 and 16 are very different. So that's basically the scientific notation. Okay, so these are basically the 3 class goals or pillars. And the first pillar is to learn science in the context of everyday materials. The good thing about learning from everyday experiences is that you have a goal. You want to understand something, right? So I want to understand how a soap bubble works. Or let's say another good example is I want to understand coffee. Now, coffee does not know what's physics or what's chemistry or what's biology. If I were to ask you, what science is the science of coffee, you might say, well, I'm pretty sure it's chemistry because there's a lot of chemicals. Yes, that's true, but that's only part of the story. What about the whole reason you drink coffee? It's because of the caffeine, right? And what does caffeine do? Well, caffeine makes you feel awake. And why does it make you feel awake? Well, it turns out that it mimics a certain neuroreceptor, the adenosine neuroreceptors in your body. And that's when we're starting to get into biology. So the science of coffee is not just chemistry, it's also chemistry and biology. And how you grind your sizes, if you grind your coffee too much, then it's you'll get a very deep flavor coffee. Whereas if you don't grind your coffee much, then you'll get a very shallow flavor. So that is linked to the area of grinds that you're exposing, and that's actually physics. So, that's just one example. That's just coffee, right? But all the examples are going to have some amount of physics, chemistry, and biology, and so this is interdisciplinary in nature. Number 2, active problem solving. Let's say traffic jams, right? Let's say you want to understand how traffic jams work. Well, it's a very complicated phenomenon. You could think about, well, traffic jams come from the driver next to me not driving well, right? That guy's an idiot, or that person doesn't know how to drive well, right? It could be, maybe you think that red cars are different from blue cars, right? Maybe all the red cars drive in a certain way, whereas all the blue cars drive, and it's the combination of these cars that cause traffic jams. Well, you know that's not always true because ultimately it's the driver that matters, right? So this is a good example where you'll understand that ultimately traffic jams come from driver-driver interactions. And while individual drivers are very different, it turns out if you put a certain number of drivers together, they'll behave in a very predictable manner. So something as complicated as traffic can be understood by simplifying it into its most basic parts. And whether you're interested in academia or industry or whatever it is, problem solving is very important. Okay? Finally, we learn to integrate concepts into a physical or a scientific worldview. Um, my idea about this is what will you finally take away from the course is not just knowing what the course is teaching you, but also this goes back to the previous point of solving complex problems. It's basically when you see something that's going on in the world, right? You'll be able to understand why it's happening and whether this sounds reasonable and how you might make a difference. All right. And so how are we going to reach our goals? We're going to have basically 20% of group work. And I will go through how that group work is going to be done over the next few classes. We're going to have 20% of assignments, 30% of weekly labs. So some of these labs I would go and do in person as that's a certain requirement. But I want you to understand that it is not required for you to come to labs because I'll be recording these labs while doing them. So I suggest you to look at the recordings, but you don't need to come to labs. And in case you do, in case you feel that in-person is necessary, then I'd suggest you definitely have to wear face masks, right? That's a requirement. And then the midterm and the final will be 10% each. They'll be virtual. And also at the end of the class, we'll devote a couple of weeks to your favorite soft material presentation or favorite everyday material presentation. And this, you guys could choose, you will be in groups of 4 or 5, and this is where you could really have fun and make a really nice put together presentation. Last semester when I did this course, I was pretty surprised at how good the presentations are, and I actually learned quite a lot. For example, the average American eats a ton of ice cream every year. I don't even remember the number. It was something ridiculous. Okay, so this is sort of an icebreaker quiz. Basically, trying to familiarize you with ratios and length scales and scientific notations, and also just simple Googling. So let's say you have a football field, right? A football field is of a certain size, and that's a large size, right? But if you compare it to something even bigger, like the Earth, note this is not the scale, but the Earth is bigger. So if you compare a football field to the Earth, of course the Earth is much bigger. And if I told you that the ratio of the length scale of the length of the football field to the diameter of the Earth is the same as the diameter of the nucleus to the size of an atom. So basically this is a problem where the football field size, or you can Google it, the diameter of Earth, you can Google it, and I tell you that the size of the carbon atom is 10 to the negative 10 meters, and I'm asking you, well, what is the size of the nucleus, right? And so you basically divide A over B and equate that to C over D, and you find C, right? Okay, that's it for this lesson.